All right, class, let's finish up this gases chapter. Before I finish the gases, now I want to quickly go over your gas experiment in lab, and you'll see why I'm going to do that, because that's going to help us in lecture too. So basically what you're going to do, you're going to add a metal. It might be magnesium and some sort of metal, and you're going to add it to water, and you're going to produce H2 gas, and then you are going to do calculation with that gas that you just produced. Now, what is going on in lab is that you're going to have a burette. You have to have it upside down. You have the magnesium over here. You have water in a burette, and then over time you're going to produce gases. Now the thing is that because gases have very small density, it's not really practical to collect gases. So if the gas is insoluble in water, the way we collect it by water displacement. Again, the gases have very small density, so it's really hard. It's not practical to collect gases and then do analysis. So the way we do it, we just collect them by water displacement. So what's going to happen? So over here, you have the magnesium and you have water. Water plus magnesium, H2 gas is going to be produced over time, right? So over time, what I'm going to have H2 gas. These are H2 gases. Over time, H2 gas is going to be produced. And as the time goes on, you see how the volume of the water is going to go down and is going to get displaced by the H2 gases. So what I'm doing basically, I'm producing the gas and collecting them over water. Okay, now I'm going to go over this one more time. I want to make sure you really understand the concept. So gases have a very small density. It's not very practical to collect them and then do analysis. What I'm going to do, I'm going to collect them over water, do a water displacement. Here's my metal plus water is going to produce H2, right? Now over time, as more and more H2 getting produced, the volume of the water goes down, and then the gases get replaced. There's a water displacement going on. You have more gases and the water gets displaced. So far so good. Okay, now and then these are my H2 gases. Now here is a problem. There's one problem with it, and the problem with that is if I have water liquid, if you have a glass of water, you have it sit there, you come back the next day, the volume has gone down because some of the water liquid will turn into gas, will turn into vapor. So here I have, these are my H2 gases, but I also have some water vapor in there as well. So the blue is my water vapor, and then the black one is my H2 gas. So over time, again, the water is getting displaced. I'm producing some H2 gas, but the problem is, okay, yes, I'm producing H2 gas, but some of the water liquid will also turn to gas. Some of the water liquid will also turn to gas. So what do I have here? What I have there, my P total is going to be the H2 gas that is producing, but also some of water H2O gas, because over time, some of the water will also evaporate and it goes through H2O vapor. So I have both of them at the same time. So far, so good. Okay, now ready to do our first practice problem. Here is our first problem. Okay, now here when he says that we have a metal Fe is exposed to excess water, and the volume of H2 gas is collected over water. This is my key phrase, is collected over water at the external pressure of 700.0 millimeters of mercury and 30 degrees Celsius. Okay, this is exactly what we just talked about. You add a metal, you have water. What happens is you produce some H2 gas. Here at the beginning, after a while, you produce more and more H2 gas. So that's how you collect gases. You collect gases over water. There's water displacement. Now, but the other thing that you have in there, you also have some water gas that is going to convolute it. Okay. Now, here's the problem that relates to that. Now, I know it's a gases problem. We talked about every time you have gases problem, you're going to write down PVNRT. This is a gas problem. I'm going to write down PVNRT. Then, is this a changing problem? It's not a changing problem. No, none of the properties are changing, right? So it's not a changing problem. So it's a straight up PVNRT question. So far, so good? Okay. Now, so I know it's a gases. I'm going to write down PVNRT. It's not a changing problem. So it's just straight up PVNRT. It's not a changing problem because nothing is really changing. All right. Now, what is the variable I'm looking for? I ask you for the volume. So volume is what I need to isolate. So volume is going to equal nRT over pressure. Okay. Now, one at a time, we have to plug it in. Now, let's talk about moles first. Again, we're talking about gases. Ideal gases is for gases, right? We're talking about the H2 gas. This is what we're doing PVNRT for. I need the moles of H2 gas. It's not given to me, but I can figure it out because what is given to me, the grams of Fe, right? So I have 1.00 kilograms of Fe. And probably what you're sharing right now is like, I know how to do this. Stoichiometry, #mole ratio, right? Because they give you this, you can easily figure out the moles of H2. Now, I don't like kilograms because I like grams because molecular weight are in grams. So 1 kilograms is 1,000 grams. I like that because in kilograms cancels out. Now I can do a conversion between mole and gram. 1 mole of Fe is 55.8 grams. So I just use a molecular weight to cancel out the gram. And then I don't want the mole of Fe. What do I want? I want the mole of the gas, which is H2. Now, what's the mole ratio? If you look at the equation, the mole ratio is 4:3 because remember, coefficients are the mole ratio. So if I do that, what I end up getting is 23.9 moles of H2. Okay, so that's great because I have my moles. I'm going to come over here. My moles is 23.9. R is a constant, right? 0.08206. Now, temperature. Okay. Is temperature okay? Temperature is not okay because remember, temperature has to be in Kelvin, right? Temperature has to be in Kelvin. So it's 30 degrees Celsius. I have to add 273 to it to convert it to Kelvin. All right. Now, pressure. Is the pressure the right unit? It is not the right unit, okay? Now, here is the other thing you have to think about. The external pressure is 700 millimeters of mercury, okay? So what that means is our total pressure is 700.0 millimeters of mercury. But the key in this problem that is different than the other problem is collected over water. Because when we know that when we collect something over water, the P total is what? It is the H2 gas, but also some of the water vapor is going to get there, right? Some of the water vapor is going to convolute it. Remember this. Again, yes, we have some H2 gases in there, but also the water gas is going to convolute it. Some of the water will go into the gas phase. So we need to subtract that out. Again, the key is collected over the water. So far, so good. Okay. Now, my total pressure is 700 millimeters of mercury. Now, I want to figure out what is my H2 pressure because PVNRT here is for H2 gas. Now, they tell you that at 30 degrees Celsius, the vapor pressure of water is 31.8 millimeters of mercury. So we can easily subtract out the water vapor that is in there. So 31.8. And in your lab manual, in the back of your lab manual, at different temperature, it gives you what is that value, what's the vapor pressure of water at different temperature. So if I do that, what I end up getting for vapor pressure of just H2, which is what I want, is 668.2 millimeters of mercury. You guys are following me so far? Okay. Now, the problem is I do not want millimeters of mercury to be able to plug it into PVNRT. What do I need? I need ATM. So 668.2 millimeters of mercury. What I need is ATM. You know that 1 ATM is 760 millimeters of mercury. So what I end up getting is 0.879 ATM. Okay, I'm gonna put it over here. I want to put 0.879 ATM. You guys are following me so far? Again, nothing we haven't done before. PVNRT, I'm just going to plug everything in, right? PVNRT, I'm just going to plug everything in. Okay, so now if I do everything, what my final answer is going to be in liter is going to be 676 liters. So far, so good. I'm going to go over this one more time. Again, this is a PVNRT. Gases, you write down PVNRT. It is a changing problem. It's not a changing problem. So it's straight up PVNRT. The only key though in this problem is that you have to be careful that this is collected over water. If you collect over water, some of the water molecule is going to go to the gas phase and is going to convolute the H2 pressure. So it's got the total pressure is some of H2 but also some of H2O. So we need to subtract the H2O out so we have the pressure of H2 because PVNRT is for the H2 gas that we are doing right now. So we convert it out and we have to convert everything to the right unit, which is moles, liters, ATM, Kelvin, and we just plug it in and we get the final answer. Okay, all right, very, very nice job. Okay, now let's go back and finish up the gases. One of the things we need to care about the gases, we need to care about velocity. What do we need to think about the velocity? Because again, what is velocity? Velocity is speed. Velocity is speed because gases are moving around rapidly at room temperature, right? Okay. So we have to care about velocity. Now, RMS, what is that? That is root mean square. Root mean square of velocity. The other way I can write it as square root of velocity, okay? And again, we talked about this over here. What does this mean? This means average. Okay. So, let's talk about this. So, I have root mean square of velocity is going to equal, here's the equation to know, 3RT over molecular weight. So every time we talk about the velocity, the speed of gases, this is the equation to use. Okay. Now let's go over this equation. The T has to be in Kelvin. You probably already guessed that. The molecular weight though has to be in kilograms per mole. Okay. And we have an R constant. Now this R constant for the velocity is a little bit different. This R constant is, and I want you to remember that, 8.314 joules over Kelvin mole. So PVNRT used 0.08206 and it had a different unit. So that's what ideal gas law R constant. The R here for velocity is a different constant. Okay. Now, Here's the equation, 3RT over molecular weight. Easy equation. But most of the time, without even plug into this velocity equation, you probably know what the answer is. Because remember, when the molecular weight goes down, when you have a lighter atom, the velocity goes up. If you're a light atom, you can run around much faster. If you're a heavier atom, you probably cannot move around that fast. And this equation shows that if the molecular weight goes down, the velocity goes up. If the molecular weight goes up, the velocity comes down. Okay, so there's a little bit of common sense in it, which is kind of nice. So that's the velocity, and this is the equation for velocity. All right, we're almost there for gases. Here's the last part. The last one I want to talk about, I mean, there's one more thing after that, but almost the last part. Graham's law of diffusion and effusion. And this is M. So, remember, when we talk about gases, we talked about it, like gases go and fill up the entire room, right? So they diffuse and then they can effuse. So that's why we have to talk about gases. Now, what does diffusion means? Diffusion is really nothing fancy. You've used that word before without using the chemistry, knowing you were doing chemistry. Diffusion is a process of gases filling the box. Okay, is a process of gases filling the box. So let's say I have helium gas and I have xenon gas. They're going to go in and they're going to fill up the box. So basically is a process of gases filling up the box. My xenon was a little upside down. Now, what do you think effusion is? Again, you used that word before without thinking about probably what you were talking about. Basically, what effusion is a process of gases escaping from the hole in the box, okay? So the gases are going to escape from a hole in the box. So I have, again, helium here and xenon here. Again, diffusion, the process of gases filling up the box. Effusion, the process of gases escaping from the box. You find a hole and escape from the box. So far, so good? Okay. Now, if we have, let's say we have two gases here, right? If we have two gases here, which one is going to fill up the box faster? Or which one is going to escape the box faster? What do you think? The one that is lighter, right? We talked about that. If you have a lighter, you can run around faster, you can find the hole faster, and you can get out. And if you are lighter, you can fill up the box faster. So the molecular weight makes a difference, right? Makes a difference. So here's our next equation, and this is the last equation. I want to have rate 1 over rate 2 is equal molecular weight 2 over molecular weight 1. This is nothing fancy at all. What this one is telling me is basically is a ratio. If I have two gases, which one is going to have a faster ratio? And you know already that the lighter one is going to be faster to escape and then to fill up the box. But again, the question is how much? So what this is just a ratio. And remember, like a minute ago, we said when we have velocity is 3, let me write this nicer. When we have velocity is 3RT over molecular weight. You guys remember that? We just talked about it over here. 3RT over molecular weight. Okay. So again, it's the same constant. Everything goes back to the molecular weight. If I have two gases in a box, because they're in the same room, they are going to have the same temperature, right? So the temperature can cancel out and the R can cancel out because it's a constant. So then if this goes away, basically what it depends on, when I'm talking about which gas is going to diffuse or effuse faster, it just will be comparing the molecular weight. Molecular weight is the only part that is going to be left over. Okay, I want to summarize it one more time for you because I just want to make sure we're on the same page. So every time we talk about the gases, we're talking about velocity because gases run around pretty fast. So the velocity, 3RT over molecular weight. And you already knew that conceptually, that if the molecular weight, if a gas is light, the velocity is going to be high. If a gas is heavy, then the velocity is going to be low. But this equation confirms that. Okay, so 3RT over molecular weight when we're talking about the velocity of gases. Now, if I have two gases to compare for diffusion, for effusion, we already know if you're lighter, you're going to run around faster, you can get out faster, you can come in faster, you can fill up the room faster. But if I want a ratio, I can just divide the molecular weight together to get a ratio. And again, if I'm talking about two gases in the same room, they have the same T, same R, the top part can go away. And again, what I'm doing, I'm just comparing the molecular weight. So far, so good. Okay, let's do a practice problem to see when we use this. Okay. So with this problem, I'm asking you about how much faster, right? So I have two gases. I have H2 and HF. Now, without you doing the calculation, conceptually first, which one is going to be faster? You know H2 is going to be faster. Why is H2 is going to be faster? Because it has a lower molecular weight, okay? So conceptually, I know that. But this question asked me how many times? So I have two gases that I'm going to compare. You already know that. I need a ratio, right? So we said the molecular weight 2 over molecular weight 1. Now, here's the thing. It doesn't matter which one you put on top or bottom, but because we know that the lighter one is going to be faster, right? So, and you want to get a nice number that tells you how much faster the lighter one is, instead of saying how much slower is the heavier one. So what makes it easier is that the heavier atom, put it on top. Put the heavier molecular weight on top. Then you can say, okay, the lighter one is this much faster. So if we do that, let's do this one together. So square root, the molecular weight of HF is 20. The molecular weight of H2 is 2. So if I do the calculation, I get 3.2. Now, what does that mean? That means H2 is 3.2 times faster than HF. Again, conceptually, you already knew that. You just ask you for numbers. Again, do the molecular weight of the heavier one on top, so you get the ratio that you can say, okay, the lighter one is this much faster. Okay, so far so good. Okay, beautiful. Now, there is the last thing I want to mention, and I want to mention this because it's some textbook they talk about this, and I'm not going to put too much emphasis on this because you already know this, but I want to just mention it just in case. If you read in the book and you're like, oh, we never talked about this. I want to talk about Dalton's law of partial pressure. Partial pressure, when you talk about partial pressure, is nothing fancy whatsoever at all. Let's say in this room, I have a pressure, right? But in this room right now, I have some H2 gas, I have some O2 gas, and I have some N2 gas, right? So each one of these have a partial pressure. When you add it up together, is a total pressure in the room. So then when they say, okay, partial pressure of N2 is nothing fancy because N2 has a pressure. O2 has a pressure, H2 has a pressure, you add them up together, you get a total pressure. But they say, okay, this is a partial pressure because the total pressure, you have to add up all this together. So when if I ask you about the partial pressure of O2, it's really nothing fancy. Just think about it as a pressure of O2 in the room. So far, so good? All right, beautiful. So next time, I want to do a very quick video. I want to summarize all the equations that we've gone over for you guys. And then I'm going to do one practice problem from my old exam. And then I want to do a little fun fact about greenhouse gases. But we are done with gases. I'm just going to do a little more practice and summarize next video for you guys. All right, good job.